Hello everybody. In this video we're going to talk about the third topic in this course, which is the chemical bonds. So just to revise what we covered before, we talked in the beginning about the atomic structure. We knew how the scientists made experiments to figure out how the electron or what are the constituents of the atom, and the nucleus, the electrons, and how the electrons rotate around the nucleus, and all this information. And then in the second chapter we talked about the periodicity of elements, and we understood how the shape of the periodic table relates to the electronic structure and how the subshells are arranged. And this kind of explained how the periodic table looks like. And then we talked about the properties of the elements based on their location in the periodic table, and we knew how we can predict the atom to be, or the element to be, reactive or non-reactive, to be metal or non-metal, or these kind of things. Here in this chapter we'll talk about the bonds that will take place between, or will form between the atoms of different elements. And this will be very related to the previous two topics. So before we start talking about the bonds, we'll talk about ionic bond, covalent, coordinate, hydrogen, and metallic bonds. These are the main famous bonds that are common bonds that are formed. There are some other bonds that are not as famous and not as common as these. But we'll talk about the electron affinity, and this is a very important term that will help us understand some of the things that happens in these kind of bonds. So the electron affinity is the amount of energy released or spent by the atom when an electron is added to a neutral atom or a molecule to form a negative ion. So if you think about it, this is gonna be kind of opposite, it's the opposite to the ionization energy or the ionization potential that we discussed in the previous chapter. So the ionization energy is the amount of energy that I need to give to the atom so that it will kick out the outermost electron. Here it's the energy that will be released by the atom to when it takes one more electron. So it's gonna be like this, and from this equation I would expect that this state is less stable than this state. So I would expect that because the energy is spent. So this state has higher energy than this state, and therefore it releases the excess energy that was there before getting this electron. And to see this, this is a very nice chart actually, and this is the relation between the electron affinity on the y-axis and the atomic number on the x-axis. And for the electron affinity, it's in the units of kilojoule per mole. And if you check the numbers, you'd see that they are negative numbers, or mostly negative numbers. Some of them are positive, but most of them are negative. And this negative number is because the energy is released. It's like the heat of reaction. If you have an exothermic reaction, the energy or the heat that's released is denoted by a negative sign. And this is just to give the reader or the observer information that this is released energy, not just gained energy. If we take a look about on the periodic table, just to remember or just to think about it before taking a look at the numbers in the chart, I would expect that this column would have the highest ionization energy. The highest electron affinity. They need only one electron to get to the stable state. So I would expect this column to have the highest electron affinity, and I'd expect the stable states to have the least electron affinity. So I'd expect the transition elements to have very low electron affinity. Because they are very stable, they don't need to get any more electrons, so they will have very low electron affinity. Also, I would expect this column and this column to have low electron affinity because they have a saturated subshell, and this saturated subshell makes them in kind of semi-stable state. So they should have this column. This column should have low ionization energy. Electron affinity, and this should have low electron affinity. And this is my intuition before taking a look at the chart. So according to the chart, you'll see that the maximum values, which is the highest energies that are released from the atoms when they get this electron, will be for the halogens, fluorine, chlorine, bromine, and iodine. And this as we expected. And we'd see the minimum or the least values would be hydrogen, neon, argon, krypton, xenon, and radon. And these are all the noble gases. And again, let's take a look at the periodic table. Let's take a look at the zinc, cadmium, mercury, and I don't know what it is. Zinc, we said zinc, cadmium, mercury. So we'll see that zinc, here it is very low. Cadmium is very low. Mercury is very low. And this agrees with what we expected. Let's take a look at beryllium, magnesium, calcium, strontium. Beryllium, magnesium, calcium. This is beryllium. This is magnesium. This is calcium. This is strontium. So this agrees with what we expect. We would expect also that this column, which is oxygen, sulfur, selenium, would be high or will have high electron affinity, but it's not as high as fluorine. They need 2 electrons, so they will be saturated by 2 more electrons. So 1 electron will make them more saturated than the case that they are in now. So let's take a look at oxygen, sulfur. Here it is oxygen, sulfur, and selenium. So again, it agrees with what we expect. The same should be for copper, silver, gold. Where is copper? Here is copper, here is silver, and here is gold. Again, it's kind of high, but it's not very high as the others. So this makes a lot of sense, and we can, again, from the periodic table, we can expect which of them would have high and which will have low electron affinity. One last thing that I want to highlight is that when we look at this column, we said in the previous chapter that this is the most reactive and this is the least reactive. Because as you go down, the electrons or the electron size gets larger, and the electron will be far from the atom, so the attraction force between the nucleus and the atom and the electron is not going to be high as it is in this case. So I would expect the fluorine to have the maximum ionization, electron affinity in all the atoms, and with respect to these, I would expect fluorine to be the maximum. And this is lower till we reach the least value here. But when we look at the chart, we'll find that fluorine is lower than chlorine. And the rest is as expected. We have chlorine, bromine, iodine. Let's see what else we have after. It's astatine, and then I don't know what it is. And astatine is here. So this is high, lower, lower, lower. But fluorine should be here. I would expect fluorine to be here, but fluorine is actually low. And this is because the fluorine atom is very small atom. Like you have a nucleus, 1 energy level with 2 electrons, and then the second energy level has only 7 electrons. So the electrons are very packed around the nucleus. They are rotating in very small volume. And the electron that's coming to saturate the atom would face some repulsion from the atoms that are closely or closed packing around the nucleus. They're forming a closed packing around the nucleus. So they would form some sort of repulsion with the coming electron, and that's why its electron affinity is not as high as we expect. It should be something around 370, 380, something like this, but we found it to be 330 or 325. And this is because of the repulsion between the electrons and the electron cloud and the coming electron. And this is all what we need to know for the electron affinity or the electron affinity. I'm sorry. I'm going to stop here, and the next video I'm going to start with the ionic bond. So I'll see you then. Goodbye.